Okay. Good, I think ready to go. Sorry for the delays. Let's jump right in. Last Wednesday was way too hot, including for this tablet. And it crashed midway through the proof. Of this satisfiability algorithm. So I prepared a bit more on the slides so that we can go through this a bit more quickly now. But I'll basically just start from the beginning again. I think this not that much that we've done before, and the recording just stops in a random place. All right, just in case there are questions on Slido, let me set this up. And okay, live stream seems running, even though not too busy. Okay. In the next section, we'll look at uses of randomization for solving NP-hard problems. In particular, we'll look at the 3-SAT problem. And so in comparison to the previous chapters, here we're really trying to find a random object that's very rare, namely a satisfying assignment. At least it could be very rare if you're given a formula that is satisfiable. It might be very hard to find the single satisfying assignment in the worst case. And we'll use random sampling for that. As a warm-up, we'll just do the 2-SAT problem. And I discussed this in more detail previously. So whenever you have a cycle that includes a contradiction, then you're doomed. And you can show that this is a characterization. The formula is satisfiable, the 2-SAT formula, if and only if the strongly connected components don't contain any contradiction. And you can turn this into a linear time algorithm. So we're not trying to solve this problem any better. All we're doing is a warm-up for what's coming for 3-SAT right after this. But it's useful to illustrate the tool, especially for the analysis, to look at this simpler problem first. The whole design methodology is called local search, and it's much more broadly applicable than this specific example. But also, as you'll see in the 3-SAT version, there's some parameters to tune, and without some idea for the analysis, it's usually very hard to tune them in the right way. For 2-SAT, life is easier. You can just take a uniform, randomly chosen assignment at the beginning, and then we locally improve it. What does that mean in this specific case? If the formula is not yet satisfied, well, I guess if it is, it's the easiest case and we just stop. But if it's not, there must be some clause that's not satisfied. It has two literals. If it's not satisfied, both of these are false. So I'm just going to pick a random one and make it true. That makes the clause true and hopefully gets me closer to a satisfying assignment. And I keep doing this for a certain magic number of times. And if I've not succeeded after so many attempts to locally tweak the assignment, then I'm going to declare this is likely not satisfiable. Now, this number of repetitions is crucial. Otherwise, you don't get a good guarantee in this case here. To summarize the properties, if the formula is unsatisfiable, we never accidentally report an unsatisfying assignment. That's clear. But if the formula is satisfiable, we might still not find an assignment if we're continuously unlucky. And so we have to talk about how likely that is. And the running time is an easy analysis because it's basically just the number of loop iterations, and I've put generously linear time for checking the formula each time without even trying to be very smart about it. The critical part is to prove claim 2, right? That if I have a satisfiable formula, I find some satisfying assignment with this probability 1 minus 2 to the minus confidence, which is a parameter we give. So we can make it extremely likely to find it if we keep going for a while. And you see that this is a relatively good dependence. If you want to halve the error probability, you just have to double the number of iterations. How can we prove this? We start with some random initial assignment. Let's call that alpha 0. And then we do in each iteration, if we're not yet done, then life's easy. We flip one variable in this alpha t to get the next assignment, alpha t plus 1. And that's all we do. We say in the algorithm we make one of the literals true, but it really means just flipping the assignment of one variable. What we'll do is we'll analyze, this is, I alluded to this last time, but a bit more cleanly. The algorithm itself is complicated because we don't exactly know how many satisfying assignments there are, so it might stop early. We don't know exactly if in a certain literal, in a certain clause, I could have picked either literal and made progress. So we'll analyze a simpler random process, W, which is certainly running for longer or never shorter than our actual local search, but which is easier to analyze. So we'll get an upper bound on the running time by analyzing a process that might run for longer. So in several places, we're making worst case assumptions and thereby creating a process that's a little bit further away from the original algorithm, but becomes easier to analyze. And the first such simplifying assumption is that if the formula is satisfiable, we know there's some satisfying assignment. Let's assume there's just this one. Or in other words, you have a specific satisfying assignment in mind and you want to hit exactly that and you don't accept any others. Let's call that alpha star. And W will only stop if we hit exactly that assignment. Now we can measure the progress we make towards hitting exactly this assignment in a much easier way, namely how many variables does the current assignment alpha t have in common with this assignment alpha star. That's expressed via the Hamming distance, but really it's how many variables do you assign to the same truth value. And that's a random variable that changes over time. And this is indeed, it's a number for now. Now, local search starts at the random alpha, but we can again make a worst case assumption and say our W has to start at the worst possible starting point, which is the complete opposite of alpha star. So we start at the negated position. Every variable is set to the opposite truth value. Then initially we have no variables in common with the alpha star assignment we were trying to hit. Then if we look at a specific clause, if it's not satisfied, then what we know about our current assignment and alpha star is that they have to differ somehow. And they might differ in, so alpha star makes this true, alpha t makes it false, but it could be that even alpha star makes only one of them true. It's not clear by how much they differ, but I certainly have to change one variable, otherwise alpha star couldn't satisfy this. But it could also be that I have to change both. This is just, we don't know. The case that I have to change both is the good case, because then my random flip will always make progress and will always increase my x, the number of variables I'm guessing correctly. So it sounds like the case where we're further away is the bad one, but if I pick the right clause, it's actually the good case, because I'm guaranteed to make progress. But in the other case, if the assignments only differ in one of the two variables, I only have this probability 1/2 to pick the right one in my local search. And so next time where we use a worst case assumption is that we'll always have this bad case where we only have a probability of 1/2 to make progress. Okay? So several cases where we picked worst case assumptions. We have a single satisfying assignment that we're trying to hit. We start in the worst possible state, and we're only making progress with the lowest of all possible alternative scenarios. That means W makes a correct flip with exactly the probability 1/2, and the flip side, if it makes the other choice, it flips a variable into the opposite, so it decreases x by 1. So these are the two options in each stage. If we're not done yet, then the new number of variables that agree in the next time step can go up by 1 with probability 1/2, or can go down by 1 with probability 1/2. There's only these boundary conditions. Now, with this definition, this is a Markov process because the probability of what happens next depends only on the current state. If you want, the original algorithm is also a Markov process, but then you have to take the full assignment, not just the number of variables that you guess correctly, but you have to take the full assignment into account. And it's I don't see how you could analyze this. But this Markov process with only the number of correct variables is very simple now. It's just a random walk where you go up with probability 1/2 and down with probability 1/2. And then it has a boundary condition at 0. You can't go below 0, so you're stuck there and have to bounce back, basically. And there's an absorbing state. If you hit k, all variables assigned the same way, then you stop. So if you keep running this random walk, it will eventually stop, because there's no way it cannot. It might run forever around, but that's with probability 0. It will almost surely hit eventually this state because of the reflective, because of the probabilities. Okay. How can we prove this? How can we analyze this random process? We'll get back to this. I'm showing the analysis in a slightly more general form than we needed. One, because while we're at it, you can do the more general form, and maybe it's useful for some other problem, but also it will be useful for the subsequent problem. The key here is what to analyze, and we'll keep things simple by looking just at the expectations. The key quantity will be this yi, which is you're currently in this state I of the Markov process. Now there's you can go up or down with probability 1/2 each, right? So I'm currently at this point, and you can go up or down, blah, blah, blah. Eventually, I might reach this absorbing state k. And so the quantity we're interested in is the expected number of steps until I reach this state. And it turns out this is well defined and can be computed. And it is in a way a recursive equation. So yi is indexed by the starting position. Now we can say a few things. Yk is 0 because we're already in the absorbing state. There's deterministically the end. Y0 all the way to the left, this is the bounce back state. You can only go back to state 1 from there, but you have to spend 1 time step. So the expected number of steps to reach from Y0, the absorbing state, is 1 for the first step, plus whatever it needs to get, whatever it takes you to get from Y1 to the absorbing state. And this works, these equations work because these are expected values, so they're linear. This y1 might do many more steps, but we certainly need this step 1, and so it's linear in, well, the term for y0 is linear in the expectation from state 1. There's also a lot of independence in this process, but we're not even exploiting that at this point. Then the general form at yi, we have probability 1/2 to go up or down. You can write down the equations for a general probability, where this is some probability pi, and then you have probability qi to go down. And the whole first step works in full generality. So probability pi to go up, qi to go down. And this is for all I between these two. Okay. Now, how can we solve this? It looks like a not so nice recurrence. But there's a cute trick that always works in this case. First of all, we do a curious thing. We write yi as pi yi plus qi yi, which is the same because these sum to 1. And then I use the recursion here on the other side. And I'm rearranging terms. So get the yi plus 1 on the other side, then, or rather, this guy goes to the other side here. Then I have pi times yi plus 1 minus yi. That's this part. And then there's these two that form into this part on the other side. And there's the minus 1, which is from the one step that we have to take. And if we now divide by pi, then we get a clean recurrence for the differences between the yi's. And I'm giving them a name here. So yi dot, sorry, there's the I missing. Yi dot is just the difference, yi plus 1 minus yi. And with a bit of abbreviation, then we get a relatively clean recursion here. Y dot I is AI y dot I minus 1 plus bi. And so if you look at this recurrence, that's a nice telescoping recurrence. This is about the easiest form of recurrence you can have. You can just insert the recursion again and again and unfold it until you reach the boundary condition for y0 dot y dot 0, again, I should say, where we have the value given. Okay? So if you unfold this, then you get this, this general solution, which is you're collecting factors of AI until you reach the boundary condition. That's the first part. And then you also have to collect all those tall terms bi that you collect along the way. And so you have a sum for all the levels in the recursion. You collect the prefactors from recursively inserting, and then you have your bi. We don't actually need that full general form. It's just cute that you can write it down. There's one more step that you can do in full generality, which is summing up all the y dot i's is actually a telescoping sum, because each y dot is the difference of one term in the previous. So if you sum up all those, you get every term with a positive and a negative sign, except for the first and last. And so summing up all those y dot j gives you just the difference between yi and y0. So you can rewrite y0 as yk, which we know is 0, minus the sum of all those y dots. And these we have in explicit form. Okay, maybe this form is not explicit enough to make sense of it, but if you plug in what we know about our p's and q's, again, okay, I have to go back here. AI was just qi divided pi, bi was minus 1 divided pi. Okay, this is, once you know p and q, these all become the same. AI is all 1, and the bi's are all minus 2. So in particular, all those products are just 1. They're just gone. That means from this formula, you get that y dot I is just minus 2i minus 1. And if you plug that into that formula here, then you get an expression for y0, which was the expected number of steps it takes you from the worst possible state to the absorbing state. That's what y0 is. You may have seen this curious sum here. I'm skipping the algebra, but it's the sum of the first odd numbers, which is always a square. So the cool graphical proof is that's 1. Then if you add 3, you can do it that way. If you add 5, you can do it that way. So it's always a perfect square. Well, what does that mean? We need k-squared steps in expectation to get from pretty much anywhere to the absorbing state, because y0 is the largest. All the other yi's are just smaller because they're already closer to the absorbing state k. If you care, you can exactly compute what their value is, but if you look at this formula, you already see it will be just k minus I squared. So our random walk W reaches this single satisfying assignment that we picked out in expectation after k-squared steps. K is the number of variables. And so also the number of iterations that it takes this local search to reach alpha star in expectation is at most k-squared, because we made these pessimistic assumptions along the way, several cases. And from that, it's the standard machinery. If you want a success probability, you use Markov's inequality. So the probability that we take 2 times the expected number of iterations is at most 1/2. And then if we do even more iterations, you could try to insert that here, but that gives a worse bound. Instead, you're grouping 2 k-squared iterations as one random trial. And then the probability that all of those fail, if you do confidence many iterations of these trials, the probability that all of those fail is 2 to the minus confidence. And that's where we get the success probability from. Okay? So keep in mind the picture here about this random walk, maybe that picture. If you have a random walk with a bouncing state 0, you bounce back from 0 into the positive states, and you have an absorbing state at k, you can calculate the number of the expected number of steps it takes you to reach the absorbing state in pretty much full generality. And there's more to be said. You can also take from this k-squared the intuitive fact that if you take an unconstrained random walk that goes up and down with probability 1/2 each, and you let it run for n steps, it moves roughly away from 0 by square root n. That's roughly the same argument. Okay. Okay. So far so good. So we can solve 2 sets. Amazing. We could already do that with classical algorithms. So how much can we push this idea further? And that's where we come back to 3 set. Let's apply the same idea and see what changes. Well, the obvious thing that changes is we have 3 literals, not 2. Clear. The key point that made the 2-set algorithm work was that the probability to move closer to a specific satisfying assignment was at least 1/2. And then we were pessimistic and said it's exactly 1/2, but that's what it was. For 3-set, this is going to go down to 1/3 because we have 3 literals, and in the worst case, we're guessing 2 of them already correctly. We're setting them to the right truth value for the rest of the formula, even though it makes them false in this clause. And we have to pick the right out of the 3 to flip the assignment. And so that's probability 1/3. There's, of course, all the other cases where we're more lucky and where the probability of success is higher. But in the worst case, that's the best we can say. Now, is that a big deal? Like a 1/3 and a half sounds not too big of a difference. You see how big a difference it is if you plug it into this random walk analysis that we've done before. So that's just copied from the previous slide, this general expression for the y dots. Now we have probability p is just a third to go up, and with 2/3 we go down. And intuitively, you already see where the problem is. This is a random walk with a drift towards smaller numbers, and we ask it to reach a large number. That's going to take a lot more trial. And exactly how much we'll see here. So we can calculate our A and our B again. I guess here the BI's same as the A's. They are all constants. But here A now is a 2. So all these products are no longer 1. They're powers of 2. And if you plug that in, so we get for yi, this product turns into 2 to the I. The other product here turns into 2 to the I minus j. And then we still have this sum to evaluate. So if you flip the order of summation, or you shift the summation a bit, you reverse the order of summation and shift it, then you're summing up the first powers of 2, which is the next power of 2 minus 1, to the I minus 1. And so you can combine these. Basically, what remains is an exponential dependence on I. So also it's negative. If you plug in this, if you undo the differences, then what you get is the sum of all those y dot j's. These are exponential in I, and we're summing them up. So again, we get the next larger power of 2 with some constant factors in front. And so now it takes 4 times 2 to the k steps, roughly, to get from the worst possible state to the absorbing state. That's not so great, because in time roughly 2 to the k, I could have just tried all assignments. Right? There's not more than 2 to the k possible assignments. And so this random process takes 4 times that long in expectation to reach the absorbing state, which means this just keeping this local search running is not gonna work. The drift is too strong. It pulls it down away from your satisfying assignment so much that essentially you would have to spend more time than the brute force algorithm to gain anything from it. So that doesn't work. But what we were neglecting here is that we're also starting at a random point. Initially, we pick a random assignment, and then we start locally modifying it. And if we're lucky, then this initial assignment is not so far away from our alpha star, and we might have a better chance of reaching that absorbing state. And that's what we're trying next. So if we wait for too long in the local search, we're only going to move away from this satisfying assignment. So instead, that's the point I just made. We're starting at a random point. Instead, we're using these local searches for a little bit of an improvement, because we can't really expect, if you just start with a random assignment, to magically hit alpha star. That's exponentially unlikely. But we can guess some random alpha and walk a little bit around for a while in the hope that that might move us by random chance closer to alpha star. But then we keep just trying with a new random alpha. That's going to be the algorithm. And by balancing out the two parts, how often do you repeat the overall process and how long do you try local modifications, you can overall improve the running time a lot. And that's what people usually say if they say local, when they say local search, is not that you just randomly modify things and hope for the best, but you balance out restarting with a random starting point and then local searches away from that point. Okay, and that's the final algorithm that pops out of this, where there's some curious constants in there that will pop out from the analysis, and you can justify them post hoc. Intuitively, the algorithm does exactly what I said. It picks many random starting points, keeps walking for a bit, and if that didn't work, it gives up and tries a new random assignment. We're going to have this confidence parameter, which is no longer used. So I modified this so that the the statement will just be about probability 1/2 to be okay, I didn't modify this. This should be just 1/2. Because confidence is no longer a part of this. It's the same argument as in the 2-sat version. Basically, a single one-sided error Monte Carlo version where you just need probability 1/2 to be correct uses that many repetitions on the outer loop. Each time you choose a random assignment and you walk for 3k steps randomly from that specific assignment. And the walking is the same as before. If it fulfills the formula because we were lucky, then we're done. Otherwise, there's a clause which is unsatisfied, and we pick at random one of the 3 literals and make that one true. And that's the local search step. Okay, so the key constants here are a relatively small number of local search steps, just 3k, no squared anymore, and a huge number, 4/3 to the k, of overall repetitions of the process. Let's see how we can analyze this. The second part, yeah, the theorem somehow this should be, I see. I think point 2 doesn't match, but okay. We'll basically show that we have probability 1/2 to be correct with the algorithm as stated here. And then if you want this 1 minus 2 to the confidence, and there's a minus missing as well. That's the same argument as before. You just treat it as independent repetitions, and the probability that all of them fail is just 2 to the minus confidence, 2 to the minus number of repetitions. Also, as before, if the formula is unsatisfiable, we're not gonna make suddenly claims about a wrong satisfying assignment. The interesting bit to show is if the formula is satisfiable, then we will find an assignment and we'll make the same worst case assumption as before. There might be a single satisfying assignment, or in other words, we pick one and then we calculate the probability that this algorithm hits exactly this predetermined satisfying assignment. And we want that to happen with probability 1/2. And so we need a claim in between, which looks at one run of the local search. So we will analyze this probability that the local search, which is just this part, one iteration of this will find our alpha star with a certain probability, and that probability is very small. Now you see the form of this term is already reflected in the number of repetitions. Maybe that last part will not be very surprising. But how do we get to this weird kind of probability? The proof is taking a similar analysis as before. We'll analyze the number of variables that we were currently correctly guessing, and we'll make some pessimistic assumptions along the way. But we have to work slightly different. So with this argument from before, we would only get a 2 to the, if we're currently wrong on I variables, we would get 2 to the I as the probability to, or the expected steps to reach the absorbing state. That's not good enough. So instead, we're doing a different analysis. First of all, we start with a random assignment alpha in each of these local search steps. And what's the expected, or what's the distribution of the number of variables that we guess correctly initially. If we start with the random alpha and we compare it with some fixed alpha star, each variable is with probability 1/2 independent of the others guessed correctly, right? So that's just a binomial distribution. And we know what that looks like. We'll come back to that. Now, conditional on having a certain value x, we'll have to climb up a certain number of steps with our local search to reach the absorbing state. And we'll analyze a very, very specific case, namely, we're starting at x. We want to reach k, or let me draw it a bit more graphically as kind of levels. We're at level x, and we want to reach. So now I have a dimension for time. This is x, this is k. So that's the number of correctly guessed assignments, and this dimension is time. So I'm initially starting here as a random variable. We'll get to analyze this. I have to eventually reach that thing, so I can walk up or down. I'm actually more likely to go down, as we know, but maybe I'm lucky and I eventually reach this part here. I'm continuing to draw the dots here for a specific reason. It's easier to analyze a very specific scenario. So first of all, we need to climb k minus x steps because that's this distance. A little x as I wrote it here. That's for sure. In general, it's a bit tricky to analyze how likely that is, but we'll pick a specific step. We'll just look at 3k steps at most. But in the analysis, so 3k is from the algorithm. It keeps trying for 3k steps. U is at most k. We'll analyze only the first 3 times u of them. So in that picture, if you take that height 3 times, so flip it down, that's where we stop, 3u. Now, what I can certainly say, if among those first 3 times u steps, there's 2 times u steps up, at least, then I'm gonna end up here above the line, if you want. So we're again analyzing a simpler process. We're analyzing a process where I'm not constrained by this absorbing state k. I'm just walking for 3 times u steps up and down, and I'm asking how likely is it that 2u of those steps go up. If they do, I certainly end up hitting the absorbing state in the actual process. But here I'm kind of pessimistic again in keeping the process going. Even if I hit before, I'm going to ignore it and keep on walking. But if I do 2 times u up steps, I'm certainly hitting the line k at some point. So that's going to be a lower bound on the probability. The probability qu, meaning I have u steps to walk up, will be, well, the probability that we have 2u up steps in 3u randomly chosen steps. And we'll lower bound this by the probability to have exactly 2 times u steps. So we're seemingly throwing away a lot of probability mass, but because of the binomial distribution, so we're in this, the binomial distribution has this nice peak around the it's maybe more like this, right? For larger, it looks ugly. Maybe like this. So we're betting to be close to the value k already. And so the probability of being to the right of this is actually mostly dominated by this leftmost point, because it falls exponentially in this far end of the tail. Well, that's the intuition, but of course it's always true if you make the event more narrow, then the probability is going down. And the probability for this event we can nicely write. That's just the probability of out of the 3 u steps to have exactly u that go down. So 2/3 to the power u, 1/3 to the power 2u. So again, a binomial distribution. Okay. Now this we'll have to analyze a bit. And we're using something here, maybe this is of general interest. I don't know, we've used Stirling's approximation many times. But here we need a slightly stronger one where you have an explicit upper and lower bound. It's called Stirling-Robbins inequality. You can write it as an equation where for every n you have some value here in front. So this is the typical term from Stirling's approximation. And then you have some term in the front here where, sorry, this is, the n is up here. Doesn't make sense. There's some value Rn, which is tightly sandwiched between 2 terms. And then, it's too small. And you can also bound this e to the Rn step term between 1 and 2. And we'll only use this part. So you could say we replace this e here with an interval 1 and 2. And then I would take the equality to mean that this is in this interval that you get by multiplying this with the constant term. Okay. So it's an upper bound for it's an upper and lower bound for factorials, which is very close to this and only differs in the constant. And the difference is only 2. We can use this to bound the binomial coefficient. So this is, by definition, these factorials. And then we use on the numerator, we use the lower bound version. And on the denominator, we use the upper bound version. What's left is the e to the n parts that cancel out because there's 3u on top and u and 2u more on the bottom. They just go away. The n to the n part, that's the 3u up here, and the u and 2u here. But then again, the u's cancel because there's u to the 3u up here, u to u, u to the 2u. They also cancel. So all that's left is this 3 to the 3u, 2 to the 2u, and a certain constant c up front, which is coming from these 2 square root pi. And I'm plugging in the upper bounds for the denominator. All that we need is some number, and it's greater than 1 over 12. Okay. So there's a fairly tight bound for this binomial coefficient, but it still has these exponentials, of course. And if we plug that in here, you see most of the 3's all just cancel because you have 3 to the 2u, 3 to the u. Those go away with the 3 to the 3u. The c divided square root u stays, and the 2 to the u is left because we have 2 to the 2u here and only 2 to the u up here. Yeah, I mean, it's just rote calculation. Not much magic needed. The key ingredient is this tight bound on the factorials, then the rest is just doing the math. So what have we learned? The probability to have this many number of up steps, despite them being less likely, right? It's still 1/3 only. We can still get a lower bound for this probability. It's exponentially going down with u, not too unexpected, but there we go. Okay. Now, this was for a specific u where we start with k minus u, where we still have u variables. U variables are incorrectly guessed. We have to average this over all possible values for u if you want. And the probability for that, that's the binomial we get from picking the random assignment. So that's, well, of course, first rewriting to get the terms nicer, but really it's, this probability is from the binomial distribution. So you have this k choose the value 1/2 to the k. The probabilities for the positive and negative outcome are the same, so it's just 1/2 to the k. And I've split off from the sum here the term for u equals 0. Because for u equals, so yeah, if u equals 0, that means we've guessed all variables correctly, and then we stop immediately. So that term we can separately deal with. All the others are here. And so now we plug in what we know for qu. That was this term. Then we move the sum inwards. So here's a few things that don't depend on u. This doesn't depend on u, and the square root u, we just say this is always smaller than putting in the largest value of u in the sum. So we pull these two terms out. And we sum from what's left, the k choose u 1/2 to the u. Now there's two more tricks. We let the sum start at 0 again, whereas this was at 1. So we subtract the first term to compensate for that. And I'm pre-knowingly inserting this factor 1 here. And then if you stare at this sum for a bit, maybe you recognize that this is an instance of the binomial theorem. Binomial theorem in general is a way to evaluate a plus b to the power n, and it's evaluated as a sum. We exactly have this binomial coefficient. So this matches exactly that shape here, where a is 1/2 and b is 1. So we can use the binomial theorem in reverse here, and we get 1/2 plus a plus b, 1/2 plus 1 to the power k. That's a cool trick, right? And that's where the 3/2 comes from. And the 3/2 and the 1/2 to the k, they combine to 3/4 to the k. And the 1 is essentially bigger than this, so you can bound that away. And what's left is this nice term. And then we use that constant c was less than 1/12. That's where this 12 comes from. And that proves our claim, which everyone has forgotten by now what it was. The claim is that one round of local search succeeds with this probability at least. And that was what we computed. Q is the probability to succeed in total. We've started with QU. What's the probability if I know where I'm starting? We lower bounded that. And then we lower bounded the total expectation. Okay, so with that, we're almost done. The expected number of independent repetitions before we see a success, standard geometric distribution argument. One trial has this probability to succeed, that's Q. If I repeat for 1/Q successes, I expect to see at least one success. The bound here is not respected, so it should be at most 1/Q. But that's that's an upper bound for the expectation, and so we can use Markov's inequality in the standard way again. We use 2 times the expected value, even more actually, and that's this lovely number. If we keep trying for that many local search repetitions, the success probability is 1/2 at least. Okay. That was that. Now you see how, maybe let me just go, the theorem was, was not stated properly anyways. You can still see the running time is essentially this, right? It's if we're not too strict, it's essentially 4/3 to the k, as opposed to 2 to the k, which is a massive reduction in the base of the exponent. Now, if you want higher success probability, you have to do this a few times, but it's basically a factor that you have to do it. At most a polynomial factor, and then you get with high probability. So this is actually a substantial reduction of the style that we've tried to get with fixed parameter algorithms. And so randomization here makes this kind of reduction of the exponential growth much easier. Okay, unfortunately, that's all we have time for from randomization. There's a cool algorithm for essentially doing max flow min cut style things on graphs, but I'm going to skip that for this iteration. So here's the official warning. But are there questions on the other parts of randomization? Karger's algorithm is a standard thing. There's good expositions if you can find if you're curious. Is there anyways good point to do our break? So let's do that here. Also Mohammed kommt meistens für beides. Der Rest der Leute, die regelmäßig da sind, sind quasi hier, mit wenigen Ausnahmen. Da es ja so rum ist, können wir uns um 1 treffen und kurz rumfragen, ob es okay ist, wenn wir es tauschen. Wenn Mohammed dann auch da ist, wollen wir uns erst die Abgaben angucken, wie wir es so die ganze Zeit hatten bis letzte Woche. Von mir aus in Ordnung. Ansonsten muss ich in meinem Raum umgucken, ob irgendjemand da widerspricht. Theoretisch ist der Slot ja frei, weil er ja vorher auch funktioniert hat, aber was ist denn heute auf dem Zettel überhaupt? Okay, lauter randomisierte Komplexitätsklassen. Das will ich ja gar nicht alles an die Tafel schreiben. Okay, time to move on. No crashes, that's good. It was lovely to do randomization, but time for the third topic that I promised you, and it's gonna be cut short a bit compared to maybe the other two, but at least a few things I want to show. In the last big part of advanced algorithms, we'll look at approximation algorithms. The big other thing you could compromise on, apart from maybe the time or being deterministic, you could compromise on the quality of the output. It's very, very natural in many optimization problems, and it's a very practical approach. And again, we'll see many different types of techniques that are somewhat generic. We'll see them on concrete examples, but often they're a bit more general. And we might this time only very briefly touch on the complexity theory side of proving when approximations are hard to get or what exactly is not easy to get. But we'll focus a bit more on the positive side of things. In this first unit, we'll cover the basic definitions and look at some simple first examples, in particular vertex cover and set cover, as kind of, they're not toy problems, that's unfair, but problems to illustrate some techniques on. Then there's a cool notion about approximation schemes where you can tell the algorithm how accurate you want it to be. And then it'll take more time if you want more accuracy. And we'll look at a few famous examples. And then we'll build on this in the next unit with linear programming based techniques, which really go very, very well hand in hand with approximations. But for now, the more elementary techniques. And first, a bit of where are we and how can we formalize what an approximation really is. So just a short recap for the notation that we've had very, very long time ago. We had this class of NP optimization problems. And a problem U is, as you see, we'll see the components in a second. It's a collection of instances, concrete instances. So U could be the problem vertex cover. A concrete instance could be a specific graph. Then for every instance, we have potential solutions, feasible solutions. So for vertex covers, it would be all vertex covers, all subsets of vertices that cover all edges. And we have a cost function that assigns to each feasible solution some cost. Vertex cover would be just the cardinality of the set. And we assume that we can check in polynomial time whether a certain instance is a valid encoding of an instance, whether a given feasible solution, or well, whether a given thing is indeed a feasible solution, and we can evaluate the cost of a feasible solution. We'll here always make the assumption that the costs are rational numbers, so we don't get into questions about how to represent real numbers. I think for all the problems we'll discuss here, that's not really an interesting distinction. And also remember, we have two problem variants. The optimization problem is the more natural that we often want in applications. We want the actual feasible solution that optimizes the cost. But we can sometimes first design an algorithm for the evaluation problem where you only get the quality of the solution, but not the solution itself. In many cases, you can easily get both, but it's cleaner to first formalize the evaluation problem. We'll sometimes do that. The whole idea of approximation is this famous old saying. If you want the perfect optimal solution, that might be hard, but if you want to get a job done, then you may have to compromise a little bit on your perfectionism. So the key thing is, what does that mean to be good enough? And so there's a few terms that I want you to use consistently. A heuristic is really just any algorithm that gives you some feasible solution for a problem, but probably no other guarantee. This doesn't mean that the algorithm always produces bad solutions, or in the worst case, bad solutions. It might just mean we don't know of a guarantee that we can prove. And sometimes that's all we can get. But the goal here is something provable. And so if you think about it, maybe you've seen the definitions before, but if you think about it abstractly, it's not so clear what really you want here. You want close, you want a good enough solution, but what does that mean? And the specific notion that we'll look at is compare the cost of the solution that the algorithm outputs to the optimal value. So opt in this chapter will always be the optimal objective value of the underlying problem. So again, goal is minimum or maximum, right? It's just a way to unify the two kinds of problems. And then we go over all feasible solutions and take the cost of those, and optimum is the best possible cost. And so if we can somehow relate the output of our algorithms, or the cost of the output of our algorithms, to the optimal cost, that's what we call approximation. And to make it quantitative, we look at the ratio. Okay, that's in short what we do. Formulate, so U, here's the full thing as we had it back then. That's an optimization problem. It has some encoding alphabet for the inputs and for the outputs, and it has what is allowed as an input, what are the instances we really care about, what are the feasible solutions, what's the cost of feasible solutions, and do we min or max in our search. Okay, optimal objective value for a problem U on a given instance X is written like this, and we'll skip those parameters when they're clear from the context. Any other algorithm that's consistent with U, which means whenever this just means A of X is always in M of X. The algorithm always produces a feasible solution of arbitrary quality in general. And we call the approximation ratio of an algorithm A on an instance X just this ratio of the cost of the algorithm divided by the optimum. And hopefully the optimum is never zero. Kind of, I think always costs are positive in the examples we look at. For minimization problems, this means that this ratio will always be above 1 because you can't do better than optimum, and so you'll be bigger than the optimum most of the time. For maximization problems, it's the other way around. Here, again, you have to somehow check what the definitions are. If you look at the literature, this is not always consistent. Sometimes people always take the reciprocal so that the values are always above 1. But I think this is more standard these days. Okay, then an approximation algorithm. Finally, the key definition of this part is an algorithm, or a C approximation is an algorithm where the ratio is at most C or at least C, depending on the direction of optimization. Let's focus on minimization problems. Then our solution that we output is at most C times as expensive as the optimum solution of that specific instance. And so that seems to be the most convenient definition to always compare with, on that specific input, what's the best you can do. Now, why the ratio and not something else? You could have said it's the optimum plus something, or apply any other kind of function. I don't think there's a clear answer to that. It turns out that the ratio gives you a somewhat sound theory and is often a useful kind of intuitive way to say you're at most 10% worse than the optimum, but this is not written in stone. Sometimes for few examples of problems, it can be more convenient to do some different function. But that's the standard definition. That's what we mean by an approximation algorithm. In the next section, let's see some first simple examples of approximation algorithms. These don't use a lot of fancy knowledge about the problems. They're more to get us started. But they're also, in a way, best possible. Recall our good old friend vertex cover. So we have a graph, any subset of vertices, so that every edge has an endpoint in the chosen set of vertices. That's a vertex cover. In formal language, you can write it like this. If edges are two-element subsets, we certainly want the smallest such, because taking all vertices always is a valid vertex cover. But how, if we're given some set C, how can we prove that that is optimal or close to optimal? Right, so you can easily check that it is a vertex cover. Amazing. You can try to solve this, we know, NP-complete problem to find the smallest vertex cover. That's not going to be practical. So we need some other way. Stay. We can't really modify the specific solution we got. So all we can do is try to get a lower bound on the optimal value. Then we can compare against that. How to do that is problem specific. Here we can do something simple. We can look at matchings. A matching in a graph is just a subset of the edges, so that if you take the same vertices and just this subset of edges, the resulting graph has degree at most 1. Or you can say it in many other things. You can say the edges form pairs of vertices, or the connected components have at most 2 vertices in them. Let's maybe do an example, right? So this is a matching. There could be isolated vertices lying around. And there could be some underlying graph that I'm not drawing, but this is a matching. What you can't have in a matching is further connections. So that's an easy definition. We'll look at different types of matchings. So just be sure to keep them separate. There's maximal matchings, or I like to call them inclusion maximal to make it a bit more explicit what we mean. This is a matching where I cannot add any further edge from the graph without destroying the fact that it is a matching. This could or could not be a large set. It just means you cannot add anything to the set. Then a maximum matching is one of maximal cardinality. So just the two terms. I'll try to use inclusion maximal and maximum to keep it separate. And finally, a perfect matching is just one where we have as many edges as we could possibly have in a graph of v and vertices. So all the vertices are paired. Perfect matching means everyone has a partner. And the perfect matching certainly is maximum, because you cannot add anything. And every maximum matching, of course, is maximal, but the converse is not true. So the good thing about maximal matchings is that they're very easy to find. If you're given a graph, you can just at random pick an edge, add it to your matching, as long as it doesn't connect anything that already has an edge, and you keep going. And if you can't add any of the edges in the graph, well, then you're maximal by definition. So very easy to find. Maximum is a lot harder conceptually. It's complexity-wise still polynomial time, even on general graphs. But on general graphs, the algorithms are somewhat intricate. So it runs in polynomial time, but not linear time. And the algorithm is a bit tricky. It's Edmonds' algorithm, or the Blossom algorithm, if you want to look into that. We won't use it, or we won't use it beyond the fact that there's a polytime algorithm. So why am I talking about matchings and vertex cover? Well, simple observation. If you have any matching and any vertex cover, the vertex cover is going to be at least as big as the matching. Why is that the case? Simple simple proof. Okay, there's this weird bug why the things jump around. Take any edge in the matching. C, the vertex cover has to contain either of the endpoints, or maybe both, but certainly one of them. And also, all the matching edges are disjoint as sets. So if I'm trying to cover all edges in the graph, I have to cover all the matching edges. And for the endpoints, I know that they're in the matching edges, they're only usable for covering one matching edge. So I need to pick one endpoint per matching edge in any vertex cover. So C must have at least as many vertices as M has edges. Okay, simple. Again, little picture. If this is your matching, even if it's not maximal, there could be many vertices that maybe have some some connections in the underlying graph. Let me draw the underlying graph as well. I don't know if you can see any difference. So let's say the matching is the red thing. Then to cover the red edges, you have to pick one of the endpoints, but because they're disjoint, you have to pick one each to do a vertex cover. There's no way around it. Okay, that's an easy observation, but it means we can get a simple approximation algorithm for vertex cover as follows. Find an arbitrary maximal matching. We can do that with this greedy algorithm that I just sketched before. Here it's spelled out. You start with the empty set, you go through the edges in some arbitrary order and try to add each. And if that is no longer a matching, then you discard the edge, but if it is, you keep it. Now what's the output? You take for every matching edge both endpoints into your vertex cover. And that's going to be a 2 approximation for vertex cover. Why? Well, 2 things we have to show, right? One, the output is indeed a vertex cover, so we call this C. Suppose some edge was left uncovered. So there's an edge here that I'm not covering, but I took from all the matching edges both endpoints. So they might lie somewhere here, but I didn't take either of those 2 endpoints. Well, then I could have added this edge to the matching without violating that it is a matching, and that's a contradiction to how we pick things. So it has to be a vertex cover. And second, the fact that it's a 2 approximation follows from this lemma. Every possible vertex cover has to be at least as big as our specific matching, even if that's not a maximal one. And so we only do twice as bad by picking both endpoints. So our C is 2 times this, and we know that opt has to be at least M. So you could puzzle together what C divided opt is by using here we have exactly, sorry, here is an equal, so it's 2M, and for op we use the upper bound, so we get 2. Okay, that's a very easy approximation algorithm. And as a first example, maybe that's all we do. Now, it feels like you should be able to do better than this very simple algorithm. Maybe all we need is a closer analysis of this specific algorithm. But it turns out that's not the case. And an interesting tight example is the complete bipartite graph, where you have all edges between the left and right points. So everything is connected, but there's no edges between the red and the green side. Bipartite means you can split the vertices into two sets so that there's only edges between the sets, not within the sets. A maximal matching could be this one. And because it's a complete graph, everything's symmetric, you can always pair up vertices somehow. You can always find a perfect matching in this graph. So that will be M, and you'll output all vertices in your greedy algorithm. But of course, you could have just picked all the red vertices, and they have to cover all the edges because there can't be edges between the green vertices alone. For example, this would have been enough. So here, any algorithm that starts with matchings will end up with this factor 2. And with a bit of an extra assumption, without getting into what that is, there's a conjecture. If you assume that that conjecture is true, then people have proven conditional on that. There's no constant factor you can improve upon this 2. You can do a 2 minus some function of the input size approximation. But if you want epsilon greater 0 and a constant, that's unlikely to exist for vertex cover, which is somehow striking that this very simple algorithm that we just proved correct on one slide is the best you could hope for in the worst case. It's a bit disappointing maybe, but that's what the worst case looks like. There's 2 minutes left, which it's not going to be worth starting the next chapter in full. Let me just teaser what we're doing next. We'll look at the problem called set cover. You should really think of it as a generalization of vertex cover. In vertex cover, we have sets, which are the neighborhoods of vertices. And we're trying to cover certain things, which are the edges. So we have to pick neighborhoods of vertices, and we want to cover all the edges with that. And if you formulate it like that, why do you have to have a graph? Why would not some more general structure also be okay? And that's what the set cover problem looks at. And it's a good problem to test out more interesting facts. I mean, vertex cover seems from an approximation perspective a bit too boring, right? It's almost settled at this point. And set cover is a bit richer, and we'll see that you can also use it to model other problems. But let's do that tomorrow.